All right, so last week we spent quite a bit of time talking about the basics. I know maybe it didn't seem like basics, but they were the basics of Newton's second law. Okay, we started going over some of the different applications. We looked at elevator problems, differential acceleration method, okay, vector sum of all forces, where we had to do trig. All right, so we've looked at a lot of different kinds, not all of them yet, obviously, but we've looked at a lot of different kinds of Newton problems. And we ended off, we were looking at problems to do with systems. Okay, and we had done the problem with the two sliding boxes, okay, and how we could find the net force on the system, we could find the net force on individual parts, but the one thing that was the same for both parts was what? Their acceleration. Okay, in any system, the two parts have to have an acceleration with the same magnitude, not necessarily the same direction. Now, in the one that we looked at, it did happen to be that they were in the same direction because they were being pulled along a level surface. But in this situation, we have a system. The magnitude of the accelerations of those two masses, even though they're 10 kilograms different, is going to be the same. The direction of those accelerations is going to be opposite. One's got to go up and one's got to go down because one's heavier than the other. All right, so I want you to write this one down, draw the picture, okay? Get a free body diagram done, see if you can get started on this. All right, I will tell you that because the pulley is frictionless, the only force/forces that are acting in this problem are gravity. Okay, the only force in this problem is gravity. All right, give you a few minutes. All right, so here's what we got to remember, is that the acceleration of both the 35 kilogram and 25 kilogram mass are the same because they're part of a system. So what I want to do is find the acceleration of the system and then put the proper direction on each mass. All right, so essentially a free body diagram of this is going to look like, all right, I've got gravity here, okay, and I've got gravity here. This force of gravity is obviously going to be less because it's a smaller mass. Okay, so if we calculate the forces of gravity there, we'll have 35 times 9.81, okay, which is 343.35 newtons. Okay, and then 25 times 9.81 is going to be 245.25. newtons. Okay, at this point, I want to simplify this diagram. Those are the only two forces involved, and I'm trying to find the acceleration of the system. How much mass is in this system? 60 kilograms. Okay. So I'm going to draw the system. 60 kilograms being pulled this direction by 343.35 newtons, and this way by 245.25 newtons. Okay, that's essentially what's going on here. I have two opposing forces acting on this system. Now, granted, they're both down and I've drawn them as left and right, but that's fine. I'm just trying to find the net force on the system so I can find the acceleration of the system. Okay, so net force is the vector sum of all forces. So that'll be 343.35 minus 245.25, which should come out to 98.1 newtons. Okay, everybody all right with that? So I have a net force of 98.1 newtons in this question. Can I now find the acceleration of the 60 kilograms worth of mass in the system? Okay, so then I go acceleration equals F net divided by mass. Okay, and I just go 98.1 divided by 60. All right, so we're looking at 1.6. We only have two significant digits, so 1.6 meters per second squared. That's the acceleration of the system. I actually can't put a vector on that right now because the system is actually moving in two different directions. Okay, so in this case, I can't put a direction on that. But the question asked, determine the motion of each object once they are released. Okay, so I would separate this and then say the 25 kilogram mass will be 1.6 meters per second squared up, and the 35 kilogram mass will be 1.6 meters per second squared down. They have the same acceleration, but they're in different directions. Okay. Again, the key thing here, and it was key when we did the boxes dragging along the floor, was that they both have the same acceleration. Okay. In the boxes question, I found the system as a whole and then broke it up into the two parts. Okay. And I kind of did the same thing here. I found the system as a whole, and then I applied it to the two parts separately. Okay. Questions on how that one worked? All right. That one is a lot like what we just did. Like basically it's the same. Give that one a try. Okay, it's going to tell you the mass of the pails, and it's going to tell you the mass of the tire. Right, you got to figure out the acceleration of the system. Okay, acceleration of the system, and the table is frictionless. Okay. So what's the only force acting in this system? Gravity. Okay, so gravity is pulling on pail B as well as pail C. Okay, so pail C has a mass of 6 kilograms. Okay, so that's 58.86 newtons, and then pail B is 8 kilograms, so that's 70.48, right? 78.48. Okay, newtons there. So those are my only two forces. Now I've got to calculate my net force, but I have to calculate the net force acting on the system, not on individual parts here. Okay, so I have these two masses as well as the mass of the tire, okay, which is 20 kilograms. So I got 20 kilograms plus another 14. Okay, this is a 34 kilogram system being pulled this direction by 58.86 newtons and this direction by 78.48 newtons. Okay, so we should have 19.62 newtons as our net force, right? So we'll have 78.48 minus 58.86, which will give us 19.62 newtons as our net force. Okay, now that I have that and I have the mass of the system, I can calculate the acceleration of the entire system. Right, so we would go 19.62 divided by 34 kilograms. Whoop. All right, so we're looking at 0.58 meters per second squared. And that's all I can write. I can't give it direction. Or can I? Actually, I can't. One pail is moving down, one pail is moving up, and the tire is moving to the left. So I can't give a direction because all parts of the system are moving in different directions. But the magnitude of the acceleration, which is what they ask for, is 0.58. Okay? The reason they say only the magnitude is because it is impossible to tell the direction as parts are moving differently. Okay? That's starting to make some sense. Right? Because when we do our lab on Newton's second law on Thursday, it's going to be a pulley system. It's going to work similar to the pulleys that we've just looked at. So we've got to keep that in mind when we're putting that together. All right. What I want you guys to do now is I want you to get a little bit of practice using Newton's second law with kind of entry level, moving towards tougher problems. So we're going to go to the workbook. And you're going to work on the first page of Newton stuff. Okay, so Newton's second law, worksheet number 1 is what you're going to be working on here. Okay, they start out ridiculously simple. Okay, they will become more difficult as it goes along. You'll have some where you might have to do some trigonometry even. Okay, but for the most part, they start out fairly straightforward. Okay, you guys can get going on those. If there are ones that give us trouble, then we'll go over them together. Okay, let's have a quick look at 13 here, guys. 13 is an elevator question. We talked about elevator questions the other day. Okay, so the free body diagram for this says that we have a tension in the cable, which is what each part of the question wants you to calculate. How much is it pulling upwards? Okay, we have a force of gravity pulling downwards. Right, we know the mass of the elevator is 1,200 kilograms, which means that the force of gravity is 11,722. All right, newtons. Okay, downwards. That's going to be the same for all A, B, and C because it's the same elevator. Right. What changes is the acceleration of the elevator. The acceleration of the elevator changes because the tension in the cable is different depending on whether it's accelerating downwards, accelerating upwards, or traveling at a constant velocity. So in part A, it tells us that the 1,200 kilogram elevator is accelerating downward at 1.05 meters per second squared. All right, so what I know right now is mass, and I know acceleration. So for part A, I'm going to calculate the net force right away because I know mass and acceleration. So I'll take that 1,200, multiply it by 1.05, and I'll get my net force. Okay, so 1,200 times negative 1.05 because it's downwards. All right, so I'm getting negative 1,260 as my net force in newtons. Now that I know that, now I can go to this. F net is also the vector sum of all forces, which is tension plus gravity. So if I want to find the tension, I'm going to take the net force and I'm going to subtract the force of gravity, which is also negative because I already made this, which was down, negative. So I'm going to have negative 1,260 minus negative 11,772. Okay. When I do that, okay, I'm going to get the missing force to be 1.05, but we'll do the operation here. So answer minus negative 11,772, right, is 1.05 times 10 to the 4 newtons upwards. Okay, that's less than the force of gravity, which is why the object is accelerating downwards. Everybody okay with that? Okay, then for part B, it's the opposite. Now, instead of having the 1,260 be negative, now it's accelerating upwards. So I just make the 1,260 positive. All right, and when I do that, okay, I'm going to have positive 1,260 minus negative 11,772, and that's why I get a bigger tension. In order to lift the elevator, the cable has to pull harder than gravity does, right? And that's what this is showing. Okay? Because the force upwards is greater than the force downwards, the elevator accelerates up. Now, for part C, that requires no math at all. Okay? In part C, you should do no math at all. It's moving downward at a constant velocity. If there is a constant velocity, what is the net force? Think Newton's first law. 0. It's not accelerating. Therefore, the net force is 0 because the acceleration is 0. So that means that since there's two forces, this one, and they're opposite, they must also be equal, right? The only way for the net force to come out to 0 is if it's pulling upwards and downwards with the same amount of force. Okay, so that one requires no calculating. You already calculated the force downwards. You make the force upwards the same but opposite. Okay, does that make sense? All right, so that's a very typical elevator question. Right? I usually put one like that on your major assignment, sometimes on your test. Okay. Any other ones giving us trouble? Okay, I want to go over a different example here. Okay, this is what we call a static condition example. Static condition is exactly what we just did in part C of the elevator question. It's static because the object is not changing its velocity. So static questions involve a net force of 0. Okay, so this store has a sign that has a mass of 35 kilograms, and it's hanging from 2 different buildings. Right? Cable 1 is angled 55 degrees below the horizontal from one wall, and cable 2 is attached horizontally to a different wall. Okay, so what we have is, here's the first building, and this is the toughest part, is drawing this picture. Okay, I've got a cable, and it's angled 55 degrees below the horizontal. And then I have another cable that's stretched straight horizontally and attached to another building. Everybody with me so far? All right, so the sign has a mass of 35 kilograms. It's being supported by tension in this cable, so that's a force, and tension in this cable is pulling horizontally, that's another force. All right, what force am I missing? What else is pulling on the sign? Gravity. Okay, so I would have a gravitational force here. Okay, 35 times 9.81 should be 343.35, right? Newtons, I think. Someone can double check. All right, so that's what I've got. Those are my forces. It wants to know what's the tension in this cable, right? So that's cable 2, this is cable 1. So right now you look at this and you go, crap, there's not very much information here. Okay, but the most important piece of information is not one that's outright given to you. This sign is hanging there. It is not what? It's not moving. So as a result, this force, and this force all add up to 0. Okay, this cable here can only pull to the right. Okay, so if it's not moving, where's the left force coming from? Yeah, from this one. Okay, this one's angled, which means it's pulling to the left and it's pulling up. Okay, everybody with me so far? All right, so whatever the tension in cable 2 is, it's got to be equal to this one, because that's the only other force pulling horizontally. Now, this vertical force has got to be equal to what force? Gravity. All right, so now I know this side here is 343.35 newtons. So now I've got a triangle where I know an angle and a side. Okay, it is trig. So can I find this side of the triangle? And that side of the triangle is equal to the number they want me to look for, right? The tension in this cable, which is cable number 2. All right, so in this case, the question doesn't tell you much. You have to really pick it apart to get the things you need. You have to realize it's not moving. So the net force is 0, which means as long as I can find components, they add up to 0. And I can use those to find other things. Okay, so what I'm going to do here is find this side of the triangle using trig. I'll use tan because I'm using the opposite side and the adjacent side. Okay, so the tan of 55 degrees is going to equal the opposite side, which I know, 343.35, over the tension I'm looking for. So I'm just going to divide the 343 by the tan of 55. And that should give me the tension in the other cable. Okay, so 343.35 divided by the tan of 55. Okay, so there's 240 newtons of force in cable 2. Okay, pulling to the right. Right? That's about as complex as they would get. Okay, in terms of, here's the situation, figure it out. There's a lot of figuring in there. There's a lot of intuitive leaps that have to be made to answer a question like that. But what you have to remember is that it gave you one very important piece of information, not directly, but it gave it to you, and that was that the net force was 0. Okay, so whenever you read a question, if it seems like it doesn't give you enough or very much information, read it carefully and see, is the object even moving? If it's not, then you know all the forces add up to 0. And that's another piece of information you can use, okay, in terms of the vector sum of all forces. Okay, so that's where we're headed. Okay, not there quite yet, but that's where we're headed. The questions are not more mathematically difficult. We had to calculate this number, and then we had to do one trig calculation. There were only 2 calculations in this question. Okay, mathematically, that's not a difficult question, but there's a lot of intuitive leaps that had to be made to get there. Okay, that's the hard part, is those intuitive leaps. All right, try this one. You've been doing ones like this. This is a system question. It's a lot like what our lab will be like on Thursday. Okay, so we got a 4 kilogram mass sitting on a table. Okay, the friction on the table is 32 newtons. And there's a 5 kilogram mass hanging over a pulley attached to the 4 kilogram mass. See if you can figure that one out. First step in solving this one is to identify all the forces acting in the system and determine which ones are important. Okay, obviously one of the most important forces in this system is the force of gravity acting on the 5 kilogram mass. Right? Without that, this system doesn't move. In fact, that is the driving force of this system. So the force of gravity here, 49.05 newtons. Okay, so I've got that force. Okay, then if I look at the 4 kilogram mass, okay, yes, gravity's pulling on the 4 kilogram mass, but the table is pushing back up, and those two forces do what to each other? They cancel each other out. So I'm not even going to bother with those two forces. Okay, they're not important for what I'm doing. I'm going to take them right off. But what I do know is that there's a force of 32 newtons, which is friction, resisting the movement of the 4 kilogram mass. So there's only 2 forces. Gravity pulling on the 5 kilogram mass, friction pulling on the 4 kilogram mass. So if I want to find the acceleration of this system, what I essentially have is a 9 kilogram mass being pulled this way by 49.05 newtons and this way by 32 newtons. Can I find the net force on the system? I just subtract those 2 numbers, right? So that'll give me (49.05 minus 32). So my net force is 17.05 newtons. That is acting on, as we said, 9 kilograms worth of mass. So the acceleration of this system is 1.9 meters per second squared. I can give no more than that in terms of information because that's the acceleration of the system. Now, were I asking this question on an exam or a quiz, I would throw this in to try and catch some of you. I would ask, not calculate the acceleration of the system, I would ask calculate the acceleration of the 4 kilogram mass. Why would I do that? Exactly, I'm trolling you. I'm trolling to find out, okay? I'm trolling to find out how many of you remember that the acceleration of the system is the same as the 4 kilogram mass. And you know what? I'd catch between 1/3 and 1/2 of you on that, okay? Because what would happen is you would go 4 kilogram mass. Okay, instead of calculating acceleration the way we did, which was F net over the mass of the system, that was the 17.05 over 9, a bunch of you would divide it by 4. Because I put it in your head at the start of the question that I only cared about the 4 kilogram mass. And you'd forget this is a system and all of the mass has to move. That's what I would be doing, okay? But does it make the question any harder? It doesn't make it any mathematically harder. I still have to do the same steps. The only thing that would change is once I know it's the 4 kilogram mass, I add to this number right or along the table or something that implies I'm talking only about the 4 kilogram mass. It's those little things, guys. There's so many small details we have to always be aware of in these questions. You will have a quiz tomorrow. It will be on Newton's second law questions like the ones you did today. So I would expect an elevator possibly, okay? But I will post that quiz, same as I always do, okay, around 3:30 today. Make sure you check it out tonight.